We demonstrated in segment 3 how oil was used in turbine operation to lubricate bearings and remove heat. In this segment, we'll see how oil is used to operate stop valves, control valves, reheat stop valves, and intercept valves. The primary function of these valves is to control steam flow through the turbine during normal operation and to shut off all steam to the turbine during shutdown or emergency conditions. When a turbine generator is connected to a power system and producing electricity, its speed doesn't change. Speed is held constant by the power system. Then the valves are opened or closed to increase or decrease generator load. However, when the turbine is not attached to the power system, turbine speed does change, and a very fine system for speed control is required. And that's what we'll be talking about. A system that works to control the speed of a turbine when it's not connected to the power system. Now, later on in your training, we'll be going into more detail. Then you'll learn how the load is controlled when the turbine is attached to the system. For now, though, we'll discuss the basics of speed control on a turbine that's not attached to the power system. Now, there are a number of systems that are used to control turbine speed. The two most common systems for control are the mechanical hydraulic control system and the electro-hydraulic control system. The essential difference between them is that the mechanical hydraulic control system uses oil from the main lube oil system and a mechanical governor for controlling turbine speed. The electro-hydraulic control system, on the other hand, uses an independent oil supply and an electronic governor for control. Now, while there are unique aspects of each system, their principles of operation are the same. In this segment, we'll use a mechanical hydraulic control system to show you control system principles. Oil is supplied to our typical mechanical hydraulic control system by the main lube oil pump. Now, you saw this drawing in the last segment. Here's the main lube oil pump, here's the booster pump, and here's the oil reservoir. A typical flow path is as follows. The main lube oil pump receives oil from the booster pump, located in the reservoir. Oil pressure is increased in the main lube oil pump so that it can be used to operate the control system. Once the oil has passed through the control system, it is returned to the reservoir to be used again. This overall system is usually called the turbine lube oil system. It, too, is a closed loop. Now that we know where the oil comes from, let's look how it's used to control stop valves, control valves, reheat stop valves, and intercept valves. All four types of valves are operated by hydraulic actuators. Hydraulic actuators differ slightly in design depending on the type of valve they're controlling. However, they all work pretty much the same way. In order to describe how hydraulic actuators work, we'll use this simplified version of a typical control valve hydraulic actuator. A stem connected to the control valve enters the hydraulic actuator and is attached to a piston. The piston is located within a hydraulic cylinder. Above the piston is a spring, which applies downward pressure on the piston to close the valve. The action of the spring can be countered by allowing high-pressure oil to flow below the piston, pushing up. By varying the amount of oil in the hydraulic cylinder, the valve can be positioned fully open, fully closed, or at any point in between. For example, to close an open valve, the oil is allowed to bleed off from the cylinder, and the action of the piston spring closes the valve. Turbines are usually operated at a constant speed, normally either 1,800 or 3,600 revolutions per minute. If turbine speed changes from its desired value, a device in the control system senses the change and signals one or more hydraulic actuators to compensate by adjusting the control valves. The sensing device is called a governor. In the mechanical hydraulic control system, the governor is a mechanical device. One such device is called a flyweight governor. In the electro-hydraulic control system, the mechanical governor is replaced by an electronic governor. The governor sends a signal to the control system. This signal indicates the turbine speed and is used to regulate the control valves. A second governor is usually installed to function at abnormally high speeds and operate the intercept valves. In effect, the governors control the flow of oil under the hydraulic actuators for either the control valves or the intercept valves. For now, we'll just consider the operation of the control valves. If turbine speed drops, the control valve opening must increase so that more steam can flow through the turbine. This means that the governor must cause high-pressure oil to enter the hydraulic cylinder, pushing the piston up, opening the control valves. Conversely, if the turbine speed increases, the opening of the control valves must decrease, reducing the flow of steam and turbine speed. This means that the governor must cause high-pressure oil to be bled from the hydraulic cylinder, allowing the spring action of the piston to close down the control valves. If the turbine speed remains constant, control oil must be trapped in the hydraulic cylinder so that neither the piston nor the control valve will move. Well, now that we understand what has to happen, let's take a look at how it happens in a typical mechanical hydraulic control system with a flyweight governor. Here is the flyweight governor, and here is the hydraulic actuator. Between them is a servo valve used to control the flow of oil into the hydraulic actuator. The flyweight governor, the servo valve, and the hydraulic actuator are connected to rods, which in turn are connected to a crossbeam. Through this arrangement, turbine speed can be accurately controlled. The flyweight governor is composed of a shaft connected to the turbine by gears so that the governor spins with the turbine rotor. Two L-shaped brackets are attached to the governor by pivots. The brackets are weighted at the top of the L and are connected at the bottom to a rod that joins the governor to the crossbeam. A spring is connected to both L-shaped brackets. If the turbine slows down, centrifugal force on the spinning governor is decreased, and the spring pulls the weights inward. This causes the bottom of the brackets to push down on the rod and the crossbeam. The combined push causes the servo valve to open, directing high-pressure oil into the hydraulic actuator. Oil pressure beneath the piston causes it to rise, and the control valve opening increases. Additional steam is now allowed to flow through the turbine, and turbine speed increases. Now notice that the servo valve position is affected in two ways. First, it's moved by the action of the governor. Second, it's moved by the valve actuator. As the valve actuator moves, it in turn feeds back information to the servo valve by actually moving it. In effect, any movement of the valve actuator results in movement of the servo. This is called a reset feature. Through this method, a certain amount of feedback is given to the control system to allow the speed adjustments to occur in small increments. If adjustments were made too quickly, the control system would fluctuate up and down while it searched for the proper speed. This search is called hunting and is undesirable because it causes rapid speed changes in the turbine. The combined action resulting from the movement of the governor and the movement of the valve actuator act on the servo valve. This results in the closing off of the oil to the actuator and freezes the control valve at a new setting. During an increase in turbine speed, the flyweight governor action is reversed. The governor speeds up, causing the weights to move outward, pulling up on the beam. Now this causes the servo valve to drain oil from the hydraulic actuator. The spring action of the piston causes the control valve to begin closing, reducing the amount of steam supplied to the turbine. Turbine speed decreases, causing the flyweights to push inward, causing the crossbeam to move down. The combined downward movement of the crossbeam and the piston closes the servo valve, so that oil can no longer escape. The control valve is now held in a new position and the turbine continues operation. Intercept valves use a similar system but have an above normal speed set point. Thus, at normal speed, they're wide open. Well, now that we've seen how the control and intercept valves work, let's take a look at stop valve and reheat stop valve systems. We mentioned earlier that these valves are either positioned fully open or fully closed. This makes control of these valves much simpler. Their actuators are like the control valve actuator we've already seen. A piston is connected to the valve, and a spring above the piston holds the valve closed. To open the valve, oil is allowed to flow under the piston, causing it to rise. When the piston is fully raised, the stop valve is open. To close the valve, oil is bled out of the cylinder. Now, besides control of the turbine, the control system performs one additional function, that of providing a means to shut down the system in the event of an emergency. Sudden shutdown is called a trip and can be triggered automatically by the system or manually by the operator. All right, let's return to our illustration. Now here you see the control system with the trip circuit included. In this simplified system, we're showing only two actuators, one for a control valve and one for a reheat stop valve. In an actual system, there is usually one actuator for each of all four types of valves. Here's the trip valve. When a trip occurs, it opens, dumping oil from all the turbine valve actuators, causing the spring action of the piston to shut off all steam to the turbine unit. Examples of condition where trips automatically occur would be low lube oil pressure, turbine overspeed, or excessive vibration. If the automatic systems fail, you should trip the turbine manually. What we've seen so far is a very simple control system. We've shown you how turbine speed is translated into a signal which determines new positioning of the control valves. Actual control systems are much more complicated and may receive signals from a variety of sources. Well, you'll be learning more about them as you continue in your training. For now, I want you to understand the basic principle of operation of these systems.